Tell me something. If the first derivative has to do with slope, and the slope has to do with increasing and decreasing, what does the second derivative have to deal with?
Rate of change of the
Good,
slope.
because the second derivative is how the slope is changing. Whether the slope is increasing or whether the slope is decreasing, that's going to give you the shape of your curve, concave up or concave down. Let's just recall how that works. So a little refresher. If your second derivative is, that means positive. Your second derivative is positive.
Slope's increasing.
What's that mean? Concave, which way? Up. That means your slope's increasing, right? Slope increasing does this. Or does this if you're going downwards. But it's going to be concave up. Well, that means that if your second derivative is negative, your
Concave
slope is
down.
decreasing. That's going to be a concave down shape. What would happen if your second derivative equaled 0?
It's going to be at a critical point.
Not necessarily an asymptote. If your second derivative equals 0, it's a possibility that
Inflection
you're
point.
changing concavity there. If your second derivative is positive, you're definitely concave up, right? If your second derivative is negative, you're definitely concave down.
Well, I guess it wouldn't be a critical point for second derivative. It would be a inflection point.
What you call that when you, well, if you switch from concave up to concave down, which we can do, right? Concave up to concave down, that's a switch. At somewhere in there, the second derivative must equal 0, right? That could be a switch in concavity. Does it have to be? Not necessarily, you need to check for it. But it's a possible concavity change. And what do you call that? Right. This is a possible inflection point. Or a hip. And a possible inflection point. So let's find out right now how to find some inflection points. That's our whole goal for the rest of our day, and then tie these things together.
Set equal to 0. And oh man, what did we do on for the first derivative test? The test if it was a critical point or not. It's been so long. Oh wait, is it right here?
So how
It's
to
on
find
the-
inflection points? We're going to be using the second derivative test. The second derivative test is going to very much mirror the first derivative test. What do you think the first thing you're going to do in the second derivative test is? We'll find the first derivative, yeah, and then geniuses, all of you, very good. Yeah, you're going to find the second derivative. So second derivative test says, of course, find the second derivative. Why are we looking for the second derivative? That kind of tells you, right? That tells you. It says if you set the second derivative equal to 0 and solve for it, you're going to get all the places where you could possibly change concavity. You follow me? Where that equals 0. Then you're going to test some intervals just like you did before. Where you're positive means you're concave up. Where you're negative means you're concave down. That gives you the way that you're changing your curve, whether you're down or up. So we do a very similar thing. You take the second derivative, you're going to set it equal to 0. For your possible inflection points, set equal to 0 for your pips. It's fun to say too. Pip. That's it. And then you're going to make your second derivative table. here's what the second derivative table looks like. And you're going to see why it looks this way when I put them together finally. You're going to have a number line that represents your graph, just like you did before with your first derivative test, just like this. Now I left this on the board for a reason so you can compare this. First derivative test goes on the top of your graph, right? The second derivative test, we're going to put right below it on the same number line. That's going to give you two things at once. It's going to give you increasing and how it's increasing. It's going to give you decreasing and how it's decreasing. It's going to give you relative max and min and your inflection points. It gives you everything right there. So second derivative test looks like this. The possible inflection points go on the bottom of your number line, on the bottom of your graph, basically. You put all of your possible inflection points, and then just like we did for our first derivative test, we're going to check a number in each interval, here and here and here. We're going to do that. Where are we going to do that? In the original function, in the first derivative, or the second derivative? This is the second derivative test, right? We better use the second derivative because that's what's going to tell us the concavity. So we're going to find the sine of each interval by using f double prime of x. I'll write that out for you. Find the sine. I don't care about the value, but the sine is important. Find the sine of each interval by using f double prime of x, second derivative. Would you like a couple examples on this? Are there any questions before we do that? Does it make sense why this is going to work? First derivative gives you relative maximum. Second derivative gives you concavity. So inflection points will tell you the distinction between the concavities. That's how we're going to use it. So let's do the second derivative test. Let's find the points of inflection, if there are any, for this next function. Find inflection points. What does it entail finding inflection points? What are we going to have to do for inflection points?
Second derivative.
So let's all take the second derivative right now. Go for it. Take the second derivative. Once you've taken the second derivative, set it equal to 0. Solve for it. Hopefully you all got that for your first derivative. Did I do that right? Do you get the same thing? Okay. Then we take a second derivative. What would this give you, by the way? What's the first derivative give you?
Slope increasing.
Slope.
Oh.
It would give you possible relative
Yeah, that
natural
would be
min, which is
close
increasing,
second.
decreasing. That's what that would give you. I'm not talking about that right now. We
Slope
will in
and
the
then
future. But for this,
how
I'm
the
just
slope
talking about
changes.
inflection points. So second derivative is where we need to be. You get 12x squared minus 24x as well? What are we going to do with that?
Plug there into 12.
What now?
Plot 12x. Set it to 0. Plot.
Set it, okay, set it equal to 0 first. Yeah. Then we're going to factor, do whatever we need to do to solve this.
Oh wait, wait.
By solving this, we're finding the places
0,
where the
2,
second derivative
because when
equals
you
0.
factor out an
That means
x-
it doesn't have a concavity. That's going to give you every possible inflection point.
Yeah.
Yes, no? How many possible inflection points do we get? Not just one, right? Not just that one, you also have that 0. So x equals 0, x equals 2.
Yeah.
Now we get to make the second
I always
derivative
forget
too.
about the other one.
Looks very similar to the first derivative test. We only have the second derivative here. And we're going to put both of our possible inflection points on that graph. It's got to be in order. It's in the
I don't know why I didn't factor out a 12. That was kind
order of a
of
number line because the graph is in the order of a number line. So the 0 has to come first
did factor out
and
next.
the 2 next. And these are our pips. Remember, that's a possible inflection point.
And plug in and
How many intervals do we need to check? Let's check all 3. We're going to check them in
Number
which one?
one.
The original function, the first derivative, or the second
12
derivative? Because
plus
that's
24,
concavity. And we're talking about
positive.
concavity here. So why don't you check that? I would probably
1,
check
12,
-1, I check 1, and I check 3. So give that a try. Remember, I don't quite care about the
Nine.
actual number. I care whether it's positive or negative. That's what's key.
9 times 12. 24 times 3.
F double prime of -1,
This is a
1,
positive.
and 3. We're going to plug those into our second derivative. We're going to see whether it's positive or negative. So -1 looks like we're going to get positive. Cool. How about 1? How about 3? What's that tell you? In this interval, are we concave up or concave down?
Oh,
Don't say concave up, all right? Concave up. Yeah. This is not concave up. Concave. So we are concave up. True? Shaped this way. Up, down, up. And we're talking about concavity. So concave, up, down, up. I don't mean increasing, decreasing, right? We talked about that earlier. Increasing means the function's going up. Concave up means the way it would be going up or the way it's going down. That's the shape of the graph, not necessarily whether you're going higher or lower, how it's shaped. That's the difference. Now, question, is that an actual inflection point?
yeah.
Does the concavity change, basically? From here to here, does it
Okay, well.
change? Then that's an inflection point. What if that had been plus and that had been plus? Would that be an inflection point? That happens occasionally, it does. Not often, I mean often it's like this, especially with polynomials, you get this a lot. But if it goes concave up to concave down, that's certainly not a possible anymore. That is an inflection point. Is this an inflection point? If I look at you long enough, you're going to change your answer? Maybe. I don't know.
I can fold under pressure.
Concave down to concave up, did it change? Then that's certainly an inflection point. By the way, is that my inflection point? That's the x value for my inflection point. Let's find the inflection points themselves.
Oh.
So I want 0 comma something and 2 comma
That'd
something
be
because that's my
like
x
in the original
coordinates of my
function.
inflection points. I have 0 and I have 2. How do you find points? Do you still use the second derivative? Do you use the first derivative or the original function? So plug that in and then find
That's
out
the
what
original
those
function.
numbers are. That's going to give you the inflection points themselves.
12.
So second derivative tells you concavity, but to find the points, you're going back to your
2. I
original
don't
function.
feel like finding the y value for 2. Let's wait for that.
Tell you what, why don't you guys handle the 2? I'll take care of the 0. Sound like a plan? Be nice to you guys. Geez, I hope I can do it now. It's a lot of pressure. Did you get 0, 12? -4? Cool. Those are my 2 inflection points. Came from 0 and 2. Those are the points. We knew they were inflection points because the concavity changes there. Raise your hand if you feel okay with this so far. Good deal. Let's try one more, then we're going to wrap all this stuff together. You ready for it? Okay, one more. But I'm going to have you do most of it. So let's start with g of x. Same question, we're going to find inflection points. X minus 1 to the 1/3. What are you going to have to do to find inflection points for this nasty looking function? Huh?
General power rule, first of all. Let's see. No, that's not it. -2. No, wait. No, that does go out in front. The exponent goes out in front. Leave this alone. -2/3 times d dx x minus 1. This be 1. Probably forgot to do
Well,
that.
what derivative, first or second? Why don't you find the first derivative first? That might be a good starting spot. Find the first derivative right now. Let's make it prettier, and then I'll have you do the second derivative. So go for it. So first derivative, what do you need to do for the first derivative here? Chain rule or general power rule, however you speak about it, that's fine. But you need to know that you're going to do the 1/3. Do you change the x minus 1? Not right now. To which power? Yeah, don't forget the power. Some people have notes on your homework. You're doing the 1/3, but then you ignore the power. That's kind of a big deal, right? So make a big deal for you. So -2/3, good.
I'll
And
just
then that's
go
it.
the inside. Alright, so I did the first one right, I think. Except.
So far, so good? Ends up being that that was actually it, because the derivative is 1, but I do need to show the work. 1/3 x minus 1 to the -2/3.
Let's try the second. It would just be the same thing again. So it would be -2 ninths x minus 1 -5/3.
Thirds times 1, because the derivative of x is 1, so that's done. That's our first derivative. Did you make it that far? Okay, now, you have an option that was like 5 people. Did you all make it that far?
Yeah.
Okay, you're getting lazy about your hand raising, aren't you? You could have the option of moving this down to a denominator, right? To a positive. However, that's going to be a little bit more difficult to take a derivative of. So with derivatives, leave it that way until you get your second derivative. So from right here, do you see you can just apply the general power rule again? Go ahead and do that. Take your second derivative from right here, if you haven't done so already. I'm seeing -2/9. You seeing that too? To the negative. Of course, that was the general power rule or the chain rule. But the derivative of that inside piece, that's still going to be just 1 for you. So let's make this thing a little bit prettier. How would we make this thing a little bit prettier? Since that's a 1, this will be -2 over
True.
9 cube root x minus 1 to the 5th. There's a lot of math right there. Can you follow that? You sure? There's a lot of stuff in our head. We took the derivative and made sure it was 1, so that's not changing anything. That's pretty much gone. -2 stays on the numerator. 9 is on the denominator. That negative exponent, that's power over root, but it's on a denominator. Power over root. Feel good about that one? What do you do for the second derivative test?
Is that equal to 0?
Okay, so 0. Now this is interesting. When's the numerator going to be equal to 0?
Or never.
It's not. It's a constant. So you don't
It's gonna be
get
equal to
any
0 in the
values from the
denominators.
numerator here. That says that nowhere are you going to have nowhere are you going to have a point on the numerator that's going to make it equal to 0. You're not going to have that value. However, we do have some points on the denominator. Do you see that we're going to have that as well? Since that's on the denominator, we go, okay, where is this going to be undefined? Where do we have an undefined second derivative? That could also give us a change in concavity. So let's look at that. Where?
1.
Yeah, that's nicely factored for you, right? X minus 1, that's the only thing that could possibly give us 0 on the bottom is x minus 1. So we know that from here, x minus 1 equals 0, that's going to give us a possible inflection point.
Well, if it's undefined, I don't think it's gonna be an inflection
Do you
point.
feel okay with this so far?
Maybe.
Let's make our table up. There's only one number. So with our one number, we've got x equals 1. That means there's only 2 intervals to check. We can check 0 for one of them. We can check
Should be a
1, or well, wherever you want to check. I would probably check 2. That's a nice number. So if we check 0,
Negative.
we're going to check it in
Yeah,
where? The
definitely.
original functions, first derivative, or second derivative? That'll give us concavity. So let's all try that.
I don't know why you wrote F.
Remember, I really care about positive, negative. That's what I care about. So when I try 0 into my second derivative, I'm going to get, oh my gosh. Negative or positive?
I said positive.
Let's try it. What's 0 minus 1?
Negative.
To the 5th power?
Negative.
Still negative. Cube root?
Negative.
Still negative. Times 9? Negative over a negative gives you a...
Wait. Oh, whoops. Wait, so is it an inflection point?
Positive.
Or did I do it wrong? The other one would be 2. And that's positive the whole time. Oh. So it's negative. Interesting.
That's concave up. That's the shape of that. Now let's do the second one. Do the second one. If I do the second one, so f double prime of 2. Plug in 2, gave you kind of a nice number. 2 minus 1 is, that's positive. 5th power, cube root, times 9. Negative value of positive, negative. Concave down. Is that an inflection point? Is that a spot where we're going to change concavity? Yeah, we're going from concave up, concave up, concave down. Yeah, for sure. Now find the point. All you gotta do is plug that number in to find the actual inflection.
Oh, I guess it's not undefined because it's only undefined when you plug it into the second derivative.
Point. So I want an inflection point. It'll be one
Very
comma
odd.
something. Where do I plug it in? Original one. That gives you points. So plug in
Zero
1,
to
and
the
1 minus 1
1/3?
is 0. Can you take a cube root of 0?
Sweet.
Is that
Say
okay?
0.
Yeah.
0 inside of a radical? Always fine.
Zero.
That's your inflection point. So this goes back to my original function, g of 1. And that's how we get that 0. By a show of hands, how many people feel okay with our second derivative test? Yeah, no? Good, all right. You ready to put it together? Do it. Yay. Let's do both the first and the second derivative test on this next function and see what it actually means. It's going to be kind of interesting to you.
First and the second.
By the way, this is the start of how you would graph a function without a calculator. Even some nasty looking functions, you can do it with this stuff, all right? I'll show you the end all of this in section, I think, 3.6, 2 sections. How you do curve sketching in general, curve sketching of anything that you really want to. And we'll be able to use all this stuff together. This is like the second little baby step. We have 2 more steps to make.
Oops. So we got -2 and 4. This is the original. 16 times 3. This is gonna be fun. Times 3 is 48. 48 minus 24. 24. Or wait. No, I'm just plugging it. I have to plug it into the original. I do, right? I think. Yeah, because if I plug it back into the derivative, I'm just going to get a 0 again. Oh, no. Okay, I'm done. I plug in a number around 4. So, 0. It's negative 5, 25, times 375 minus 30. Minus 24. It's a positive. And a negative 3. 9 times 327 minus or plus 18 minus 24. It's gonna be a positive. So. Okay, and then 6x minus 6 equals 0. Okay, we get one possible inflection point at 1. Plug in a 0, negative 6, it's a negative. Plug in a 2, that's a positive. This is concave down, this is concave up. Right. Down. Up. So it looks like that. Increasing, decreasing, increasing. Oh, I see. Cool. Very interesting.
Okay, we're going to do both the first and second derivative test, but I want you to do most of it. So right now, can you please perform for me the first derivative test? What I want to see is first derivative, set equal to 0, find my critical numbers, and make the top portion of my table. Do that. Did you get that for your first derivative?
Hopefully.
Okay. Did you
3x
solve it all the way
squared
down?
minus 6x minus 24.
Were you able to factor it, I hope? To me, it looks like we should be getting x equals negative 2 and x equals 4. By a show of hands, how many of you have got x equals negative 2 and 4? Good. You just found your critical numbers. That's fantastic.
Negative
the critical numbers
2
stand
and
for the
4,
places
yes.
where your slope could be 0, where you could possibly be changing from increasing to decreasing. So right here on our first derivative test, we got, okay, x is 4. We got x is negative 2. We're going to get negative 2. And we're going to get 4. That's our first derivative test. Now we get to plug in some numbers. So why don't you do that on your own? Plug in some values for each interval. I want maybe negative 3 here, maybe 0 here, and maybe 5 here. It doesn't have to be those numbers, but something in that interval. Remember, we're plugging these into our first derivative, not the function that gives you points. The first derivative is going to tell you slope, which is increasing or decreasing. Has anybody plugged in negative 3? Plugged it in yet? What did you get? Positive?
Yup.
Hey, by the way, in this context, What does the positive mean? Does it mean concave up, concave down,
It's
increasing,
increasing.
decreasing? And so the function is going to be going up. For this whole interval, from negative infinity to negative 2, it's going up, increasing.
It's concave down.
How about for 0? I think I'd probably do that one. Decreasing. Increasing?
Yeah.
Show of hands, how many people made it that far? Did you interpret it correctly for increasing, decreasing, increasing? So here's how this graph looks. You already have a good picture, don't you? You know this graph is going to do this. Watch. It's going to start from negative infinity. It's going to go up, increasing, until it gets to x equals negative 2. Then it's going to stop. Well, not stop. Reach a climax there. Then it's going to go down until you reach 4. Then it's going to go up forever. You with me on that? That's how this graph looks. Now, we don't really know whether it does this or whether it does this. Something funky, you know. The shape of that curve is going to be important for us as well. That's where the second derivative test comes in. So we've completed the first derivative test, told us increasing, decreasing, increasing. You probably have an idea, because it's a polynomial, that it is going to be concave like this and like that, but we need to verify that with the second derivative test. So right now, take your second derivative and do the second derivative test.
Man, 3 more videos till integrals. Come on, brother. Man.
I love second derivatives sometimes. Don't you love second derivatives sometimes? So nice. Except when they're like that. I know stuff. But quotient rules, oh my gosh, they're horrible. But for polynomials, love those things. Hopefully you got x equals 1 as well, yeah? So we're going to put x equals 1. Notice how when we combine these ideas, it is one number line because it's one graph. That means you got to put this in the right spot. I can't go x equals 1. Yay. No, that doesn't work. Okay, you got to go in between these numbers. It's like it's drawn to scale. Okay, it's your graph. So put it in between the negative 2 and the 4. It's a number line after all. Now, if x equals 1 tells us our possible inflection points, that's what that is. Let's go ahead and let's plug in some values for each interval and find out whether we're concave up or concave down. Will we plug these into the first derivative, the original function, second derivative, which one? Second derivative will give you the concavity. So take some numbers here, probably 0 and 2, plug them into the second derivative and tell me what you get, okay?
Negative.
So we plugged in 0. You got negative 6. Well, that's negative for sure. Does that mean concave up or concave down? This one, good, because if we plug in something like 2, you're going to get 12 minus 6. That's positive 6. That's positive. Concave up. So we plugged in numbers in the first derivative to give us increasing, decreasing. We plugged in numbers in the second derivative to tell us concave up, concave down. True or false? We have 2 relative extrema. True or false? 2 relative extrema. Relative extrema means a relative max, relative min. Do we have 2 of those things? Yeah, one's a relative max. Where's the relative max? At x equals what number? The relative max at negative 2. You see the negative 2? It's going up, then it's going down. Picture that.
Down, then up
Down.
would be.
That has to be a relative max. Where's the relative min?
4.
Do we know the value of those things? Not yet, but we're going to. True or false? We have no inflection points. Where is our inflection point? Okay. Here's how this tells us. If you read this, it reads like a graph. It says, check it out. You're starting out. You're going up, right? Increasing. How are you going up? Concave downwise. So you're going up, concave down. You're going to reach a point. Look at that. Concave down, going up. You're going to reach this point. It's going to start decreasing. Are you still concave down?
Still concave
Yes.
down.
Until you come to this value, then you're still decreasing, but you're starting to be concave up. You see the change there? Concave up. Then you're going to reach this point. that's going to still be concave up for the rest of the way, concave up, but now it starts increasing again. So this reads like your graph does. Increasing, but concave down. Then you're going to be decreasing, but still concave down. Till you get to here, that's your inflection point, concave up, but still decreasing, and then concave up, increasing the rest of the way. That tells you not only whether you're going up or down, but how you're going up or down. It would be different if it was like this, right? Increasing, concave up, that would be different. Decreasing, concave up, that would be different. That would be a different looking graph. So this tells you both of them, and we'll get a handle on how to do this in section 3.6 all the way through. How many people feel okay with this so far? We've neglected one thing, we haven't found the points. So I want you to find your points right now. Do the relative max. Relative min,
Do you really gotta do that though?
and the inflection point.
I know how to do that. I don't have a plan that in.
Where
It's
are you
not
gonna
very
plug those numbers into?
fun.
Good. Original will give you the points. See, we said max was at -2 something, minimum was at 4 something, inflection point was at 1 something. Does anyone have the -2 yet? 50? Double check on that, 50?
I got 60.
60?
Wait, 60. I can math.
Well, it's 10, right? I mean, who cares? Okay, how about the 4? The 4, anyone do the 4? -48? Double check? Yes?
Yeah, -48.
Perfect, -48. And the 1?
6.
6? Double check, 6? Okay, tell me what is my relative maximum? What is it though? 60. 60 is the relative max. Where does it occur? At x equals -2. What's the relative minimum?
-48.
Good, where's that
Inflection
occur?
point is 1/6.
Cool. The inflection point says 1/6. That's where the point is, that's where the concavity is changing. Feel okay about this so far? Now, before we can put all this together, we have to talk about one more section. It's kind of a long section. You see, your favorite part. We're going to go back to limits for a little bit. Your favorite.
Lame.
We're going to talk about limits,
Hate limits.
at infinity. You see, we haven't done that. We've talked about limits going to a point, but we haven't talked about what would happen if, well, we did it a little bit. We said what happens if I'm going like this, that goes to infinity. But what happens if I
As
take my
x
function
approaches
and go
infinity?
that way forever?
Yep.
Or if I go that way forever? Does it keep going up? Does it keep going down? Or does it tend to go to some number? We're going to find that out with
Limits.
limits in this section. So in 3.5,
This is kind of suck. You should have done this when we were doing limits, because man.
well, that clock's a little fast, so we still have some time. 2 over 3.5. We're going to talk about limits at infinity. I'll start off with just a little bit of a recall here. Do you remember if the limit as x approaches a number
A. Y is A.
of f of x equal plus or minus infinity,
Oh.
do you remember that that gave us an asymptote? So basically, when you could not cross out the problem on your limit,
Sure.
you had an asymptote. When you could cross it out, it's called a removable discontinuity.
Wait, let me think about that. So you got number line, A. It's approaching plus or minus infinity, so it could be like. Yeah, okay, that makes sense. Be like this or like this. Okay.
Is called a hole. This right here will give you an asymptote at the value A.
True.
And we had two cases, really. We had this case. Where we went to the same infinity, positive infinity on both sides, and said the limit existed. The limit was positive infinity there. Or we had this case, where one went up,
So that limit would not exist.
another went down. We said the limit didn't exist there. One's going to positive infinity as we go from the left, one's going to negative infinity as we go from the right. And we had a way to actually determine this, if you remember. How did we determine where we had holes or asymptotes? Sign test would do this, but how do we find out where all this stuff happens? Let's pretend we had a rational function. Rational functions have denominators. How do you find these things?
Man, how did we? I thought it was a sound analysis test. I don't know.
Okay. Let me give you an example.
Well, if it was a whole, yeah, you could factor and cancel, but it's not awesome to.
Will this have some discontinuities to it?
3 and 1.
Absolutely. Where? At 0, 1, 3. Which ones?
0.
Is 0 going to be a discontinuity?
No.
What do you think? 0? No, 0 is fine. 0 over a number is okay. That's okay.
Man, the audience is dead today.
Where are discontinuities going to exist?
No content.
3, negative 1. Why? Good, because if a denominator equals 0, you have a problem, right? That's how you find discontinuities. That's what I told you, a domain from a long time ago. So what do we do to find discontinuities?
Plug it in? That's so stupid, obviously.
Denominator equals 0. That's
Bro.
how we do it. We said denominator
Come
equals 0,
on,
we
that
solve
was
it
a trick
down.
question.
We're going to get either holes or
Actual trick
asymptotes.
question.
Do you remember when we get holes and when we get asymptotes?
Let's factor and cancel.
Maybe we'll
That's
refresh your
interesting.
memory on that next time.
They don't know? No shot, dude.
So if you
Oh
recall-
my goodness. What are these guys doing? Actual skill issue. Okay, under there. How many more? 11? Wait. No, 12. Crap. I might have to do a couple a day. Starting tomorrow, of course. Six lectures, blood. Oh my goodness. 96? Sheesh. Highest grade? Bruh. Don't even go to lectures at that point. Like, actually useless. Alright, that's it.